Okay, guys, we're going to continue is was ME design, and I'm gonna go over a couple of items that we had from our live lecture today. And I mentioned there's something regarding the project that I would like you guys to take care of, which is the life of the machine. And the life is essentially the number of cycles that the machine could last, and then you can project those into, for example, years or whatever, based on the use of the machine. And if you guys remember, the safety factor in the case of fatigue failure, we had the bunch, right? And in the case of, I think, in the case of a purely cyclic load, we said the safety factor was equal to SE over sigma A, right, which is your alternating stress. And if our safety factor in this case is greater than 1, it means that essentially we are operating below this curve, right? This is the SE of your part, and then we would be like somewhere over here, right? And in that case, our number of cycles is basically infinite, right? It will never fail. But if our stress is somewhere over here, then we said, how are we going? If the safety factor was below 1, it means that we are operating. It means that essentially our stress, right, is greater than our endurance limit, and it means that basically we can actually find the corresponding number of cycles, right? And in that case, what we did is we said we could always find our in that case sigma A is greater than SE, right? And then we said sigma A was actually equal to what? A n over B, right? And then essentially we made this guy to be equal to your fatigue strength, sort of, right? Because it's purely cyclic. And in that case, basically we said n would be equal to sigma A over A, and the whole thing is to the power 1 over B, right? And then in that case, we can find the number of cycles on a structure given that you have some alternating stress. A and B are a function of the material property SUT and the F coefficient, which we also described last time. However, this is only in the case of a purely cyclic. In the case of, let's say, you also have some mean stress, right? How would you take that into account? If you also have mean stress in addition to the alternating stress, you could basically find the life of the machine based on all the criteria that we have, and I will do it based on the modified Goodman. In that case, what we'll do is just write the safety factor equation that you had, which was equal to sigma A over SE plus sigma M over SET. So this case basically deal primarily with the case with this first portion, right, where sigma M is 0. If sigma M is not 0, if you solve here the safety factor, right, from here, and your safety factor was less than 1, it means that the structure will actually fail as a result of both of these having alternating and then mean. That also means that the structure will fail because of fatigue, but it doesn't mean that it will instantly fail. It means that it will fail with time, right? At some point it will fail. In that case, basically we can actually find the number of cycles, and in that case what we are going to do is I can actually keep this 1 over SF, right, is equal to SA, but instead now I'm going to basically replace SE with my SF plus sigma M over SUT. And remember, in this equation you can solve for the safety factor, right? If you solve for the safety factor and the safety factor is lower than 1, then we know that it's going to fail because of fatigue. But if you want to get the number of cycles, then we can rewrite this equation like that, and then we can solve for SF. And when I am solving for SF, it is like I'm solving for this SF right there, and for which I could basically get the number of cycles. So I would have SM and I would also have SUT, but now what is the safety factor? I could actually call the safety factor any number that I want, and essentially if I put the safety factor here is equal to 1, it's like I'm finding the number of cycles that the machine would last for a safety factor of 1. And I could also do the same thing if I put, instead of SF here 1, if I put 2, basically I would be finding SF, and obviously SF is always linked with an to the power b. I could be finding the number of cycles that this structure would last based on the safety factor, right? So if I solve for SF from here, I'm going to have what? So sigma A over SF is equal to 1 over the safety factor minus sigma M over SUT. So your SF is equal to sigma A 1 over safety factor minus sigma M over SUT, and this whole thing is equal to A n to the power B. So you can use this relationship to calculate the number of cycles that this machine would last, given that it has some mean stress, which is probably caused by weight or whatever, and given some alternating stress that you are impounding on a machine, for example, and then this is a safety factor for which you are calculating that number. So from here, you can solve for the number of life, or I'm sorry, the life of the machine in the case of our project. So please, you could also use that machine. Okay, next topic that we are going to be talking about in this course is going to be springs, and essentially we are going to be dealing with two types of springs. We have compression springs, which are springs that you are going to be applying forces, compression forces, right? And these are the type of springs that you would find in a variety of machinery and equipments, such as the suspension of your car, etc. And we also are going to be dealing with extension springs, and extension springs basically they work in tension. So these extension springs are always in tension, right? And then you have to, even if you apply some force on it, you won't open it up. You have to apply some force which is greater than the preload of that spring, and then that spring will open up. So depending on the application, sometimes you would want to have tension spring to keep things in tension, and then sometimes you would like to use compression springs. And the failure analysis is relatively similar, but they will differ in certain aspects. So let's actually go over it and then describe what happens when we are analyzing springs. So this is a spring. This is a spring, and if we're gonna apply whatever that we did with the case of the other items and how we analyze the fatigue failure of all these components. Basically, you have to do a free body diagram, and you have to look at the cross section or the critical cross section, and then you have to find the stresses on that critical cross section. So this is a compression spring, and we have a force. Two forces basically, compression force on top and on the bottom, and if you make a cross section, basically this is going to be your cross section on this end. So if I zoom in on this part, I'm going to have this, right, and that force is going to be over here, right? So I'm going to have a force, but at the same time I will actually have a moment, right, on this tiny element. I'm going to have a moment which is F times d over 2. So what is d? D is the mean coil diameter. Mean coil diameter is not on the outside, neither on the inside. It is just d, which is it passes through the middle of this guy, right? And then let's say you have, this is the other portion of the spring, it would be in the middle. All right, so d is the mean coil diameter, is somewhere in the middle. And basically, as a result of having this force, you know that you are going to have a moment, right? And the moment is going to be equal to how much? It will be F times d over 2. Right? So if I take that force and I move it over here, then I have to put a moment which is acting in that direction, right? So this is replacing that force, and then this will ensure equilibrium of this, right? Now, if I have this, we said last time that this is a load on that cross section. This load is going to create transverse shear loads, and the transverse shear is going to be maximum at the neutral axis, which is this is the neutral axis in this case. And then Fd over 2 is a moment which will also create some shear on this. So in the case of a compression spring, the maximum stresses are going to be in that area, and then if the spring fail, basically this is a portion where it will begin to fail most. Why? Because you have transverse shear caused by F, and then you had a torsional load caused by this moment, which is Fd over 2. Right, so here it is, right? So the maximum shear is equal to Tc over J, where T is equal to Fd over 2, C is your d over 2, and then J is equal to, we said, we had the equation for that, I think pi over 4, right? D to the power 4, which is pi d4 to the power over 32. And then the torque is equal to Fd over 2. So here, these are the stresses that we have, right? And here by taking f over a, we're taking the average shear, right? Which is simply force over area. They are not taking vq over it, but this average shear basically is going to be compensated for by adding several factors that will actually make that correct. Okay, rewriting that stress. So our maximum stress is going to be equal to, by combining the equations that we had before, your maximum shear on the spring, on the inner coil of the spring, will be 8fd divided by pi d to the power cube plus 4f pi d square. And you know all of them. You know the force, you know the diameter or mean coil diameter, and small d is essentially the wire diameter. All right. What we will have is C, which is called the spring index, which is the ratio of the mean coil diameter divided by the wire diameter. All right, and from here, what we will have is the maximum shear stress on the spring is going to be given to you guys based on this equation, KB times 8FD over pi d cube. So essentially, this average shear is being cascaded into this expression, and we are adding this KB, which is a factor that ensures that basically it compensates for the curvature of the spring, etc., to make that stress correct. So this is the maximum shear that a spring will encounter, and it's going to be equal to KB 8FD divided by pi d cube, and KB is given to you as 4C plus 2 divided by 4C minus 3, where C is the spring index. So get C, plug it here, and then take this KB, plug it here, and then this is how you can find the maximum shear stress in a spring compression spring fillet. Now I would like to look into the spring rate, right? We all know that F is going to be equal to Kx, and one thing we can do is we can find the spring rate, and the way we're going to find the spring rate is based on the energy method. So you are not really responsible for deriving this. I'll tell you that the energy in a spring is going to be equal to T squared L over 2JJ plus FL squared over 2AG, and then this comes from the energy method. If you integrate the modulus of elasticity times the stress, you will be able to get that energy. So this is similarly to what you would typically do. You know, the energy in a spring is equal to what? F x times dx, right? And or I'm sorry, kx times dx, 0 to x, and then that will be x kx squared over 2. You can replace x and then plug the force. You will end up with something similar, right? You know, x is equal to f over k, so k f squared over 2k squared, which is equal to f over, or f squared over 2k, and this is similar to here, but this applies more toward torsional energy and then shear energy. All right, so you're not really required to know any of these at this point here, but it suffices to tell you that the energy in a spring, right, is caused by the shear energy and then the torsion energy, right? Because we had two load on the cross section, so each of these load basically is somehow developing energy in that compression spring. If you take this whole energy and then you differentiate this energy with respect to F, basically you get the rate, right? Or you get the actual deflection. So the deflection is by differentiating this energy with respect to the force, you are going to end up with this expression. So we have here y, and then we have the force. Basically, your spring rate is going to be calculated from here. So K, or the spring rate, will be F over y, and it is going to be equal to this value. All right, so remember that that is your spring stiffness. And if I ask you to get the spring stiffness or the spring rate, all you have to do is simply get these values. And here again, D is a wire diameter of the spring. So usually most springs are made out of music wire, and I'm going to show you in a second how you actually do that. G is a modulus of elasticity of that material. D is a mean coil diameter, and NA is the number of active coils. Active coils is the number of coils which are being currently constrained, or which are being energized, or which are being basically loaded, right? If that spring is, if you're applying the load on a spring from here, then obviously you would start counting the number of active coils from here. And that basically depends on the ends of the spring, how the spring is basically done. So we have a diagram here. Number of active coils has to do, you have to count the number of coils, or you have to look at the total coils in the spring and then how the spring is essentially done. And here basically it shows you a little bit what that means, but I have a figure that would quickly show you or illustrate what do we essentially mean by springs closed and open. So springs have four different types, which are under two main categories. You have closed springs and then you have open springs. So for closed, what that really means, it means that the end of the spring, if you look on the spring from this direction, you're gonna see that the spring basically forms something like that. It is a pure rectangle if you are looking at the spring from this angle or from this angle. In the case of closed and plain, closed, it means that um, uh, the top helix basically is being bent to be perpendicular. So this angle right there is perpendicular. Alright, this guy is not going up. Ground, it means that the spring has been revolved like that. So you see it's touching over here, right? So that this thing, this last surface is perpendicular to the spring. So this is called closed and then plain. So closed means it is perpendicular. This guy is closed and ground. So the difference between this guy and this guy is this guy is closed, but then at the end they actually cut it again. So when you make a cut on a spring, essentially that surface here is going to be completely flat. So this is closed and ground, and that spring will sit flat in the fixture. So that is why all suspension springs are like that, because they sit flat and then they won't wobble, so they would resist buckling a lot. You could also have, so this is closed, ground, and then plain, and then the last thing is we have open. Open springs, basically this last turn is not basically bent. Instead, it is, so open, it means that, and then ground, you simply try to cut it, right? So when you cut it, you are going to end up with that surface. So this is open. Why? Because the last helix is open, is not closed. Here it's closed because this guy is closed, that guy is closed here, right? So open could be ground, and then open could be plain. So open and plain, these are the most or the cheapest type of springs, right? Open and plain. So this is just a spring that you simply come in and then cut the wire like that, right? Here you are doing this horizontal operation. Here you are bucket, or you are closing the last helix of the spring, and then here you are. This is the most expensive one, right? So this is closed and ground. So here they close it and then finally they cut it. So you have a lot of material basically, and the spring will be 100% flat. This spring here won't set flat, so that spring will always tip. This table is very useful because it relates those four different types of springs which I just discussed. You have plain, plain and ground, squared or closed, squared and ground, right? By that is the most expensive. And in the vertical column here, we can essentially relate the free length of the spring, right, from to the number of active coils. So if I gave you that spring has 2 inch, the free length of that spring is 2 inches, right? This square and then ground. So if you try to measure it and then you get that free length. If you go on here, you would know the diameter of the wire. P is going to be the pitch of that spring, right? You can find the number of active coils, and you need the number of active coils in order for you to be able to calculate the stiffness of the spring, right? So from this column, right, if you have the free length, you can get the number of active coils, and also the pitch, which is here, right? The pitch which is here, you can also find it from here. So the pitch of that spring is equal to L0 minus 2D over NA, right? So if I gave you the free length of the spring, you can calculate the pitch of the spring from here, right? So how many unknowns you have? You have NA, you have L0, and then you have P, right? So if you use this table or this column for this type of spring, like I said, if I gave you the free length of the spring, right, you would need to get the pitch, right? If you get the pitch, you can apply this. So you need to know the diameter, right? The wire diameter should be given to you. You can calculate from here the free length of the spring, right? Or you can simply take the pitch as this value. If you take the pitch as this value and then plug it here, right? What are you going to be missing? So you okay, if you take this value and then plug it here, in that case you just need the free length of the spring, right? If I gave you the free length of the spring, L0, right? And the pitch has L0 over here, you can set up an equation and then you can solve for the number of active coils. Alright, so this is a more complicated aspect of it, but there are things that are very simple here. So the solid length of the spring is when you close the spring fully. If you fully close the spring and then it's fully touching, then we know the solid length of the spring is going to be simply D, which is the wire diameter, right? The wire diameter is this, so let's say the spring is revolving like that. So this is your wire diameter, right? This is going to be the wire diameter. The solid length obviously would be D multiplied by number of total coils, right? Which is NT, alright? Again, the free length is going to be equal to that, which we already did that. Total number of coils NT, right, is going to be equal to NA plus 2. So if I gave you total number of coils, you can always find the number of active coils. Alright, so long story short, out of this table you have to identify the type of the spring. You need some information in terms of the free length or solid length, etc. And then you can get the number of active coils. Once you get the number of active coils, you can come back and then you can find this number which you need, which is called the spring stiffness, right? That spring stiffness essentially allows you to relate the force to the yield, and then this is basically K, as you guys are used to this, right? So F is equal to K times X, and then this is K of the actual spring based on the geometry of the spring, modulus of elasticity, mean coil diameter, etc. In this diagram, basically we have simple CAD drawings of a typical spring. This is closed and plane, and on a diagram they would give you the outer diameter and then they give you the wire diameter. If you want to get the mean diameter, it's going to be the outer diameter minus diameter over 2 minus D over 2. So the mean diameter is going to be DO minus D, right? This is going to be your mean diameter, which we use in the rest of the equations. Alright, so what I would like to also explain is how we essentially calculate the ultimate tensile strength of springs and etc. So for this, we have 99% of springs are made using the music wire. Alright, although we have different types of materials. Music wire is basically carbon steel, that is embedded with different alloys and copper and whatever. Right, usually people prefer to use music wire. This is the one that you see because it's usually the best and the toughest, and it is the most widely used all over the world. So the type of material that is being used in springs is called music wire. Alright, it has the highest tensile strength and then can withstand higher stresses under repeated loadings when compared to other materials. The good news here is we can directly find the ultimate tensile strength of the music wire based on the diameter of the wire. So the wire diameter is related to the ultimate tensile strength of the music wire by this factor A, which we are going to look in a second. This is the table, table 10.4 in my lecture notes, and then you see music wire is on top. We have the exponent A that you need. This is your A, and that is applicable for music wires which has diameter between 0.004 inches to a quarter of an inch. Okay, and this is the exponent that you are going to use because we said SUT was equal to how much? SUT was equal to A T to the power M, right? So M is the exponent that you get from here, so this is your M, and A is right there. Alright, and for larger, and this is for millimeters, right? So this one is in inches if you are working with inch units, and this is if you are working with SI units, and then here your diameter would have to be in millimeters for you to be able to use this M. Alright, so just be careful of that, right? So this is your wire diameter, and A is in MPa times millimeter to M. So when you get SUT from here, you are getting your ultimate tensile strength in megapascal, right? If you were using this units. There is one last thing regarding springs or compression springs is, when we find the SUT, you can also find the maximum allowable shear stress, right? And we are going to look into where you can use those and how we do the safety factors later on. We know the spring basically will fail because of shearing, right? That part here, right? So let's say this is a spring wire. We said this is a portion that is going to be subject to torsion or maximum shear stress based on the equation that I provided earlier. Your maximum shear is going to be equal to 0.45 SUT if it was music wire or a cold drawn steel wire, right? And then for other types of, if it was hardened, tempered, and carbon low alloy steel, then you would use 0.5. And the last one is for authentic stainless steel, which is non-ferrous alloy, and then in that case, your maximum shear is going to be equal to 0.35 SUT. Alright, so we are going to later on incorporate those in our safety factors as we allow the maximum allowable shear to be of a particular value in the compression spring.